Okay, welcome back, everyone. Let's continue our discussion on the convergence analysis of stochastic approximation. So the algorithm we analyze is the one we talked about last time. It's an extension of the proximal subgradient method. We just changed the subgradient to be the stochastic subgradient. So let's first show the convergence in expectation. This is the result for one iteration. If you perform one iteration of the stochastic subgradient method, then we have this guarantee. This is without expectation. So let me simplify the notation. In the proof, let's just call this stochastic subgradient as Sk. This is from the subproblem in the algorithm. So if you do one iteration, then you have this inequality, right? This is optimality with an additional quadratic term. That's what we always do. And now let's take U to be X star. the second inequality is easy. It's just this one, right? We just add the f of xk to each side. And the first one is by convexity. We assume that f is a convex function, right? So ignoring the last three terms, they're the same. And then from here to here, it's just the convexity of f. From here to here, we use the assumption that f minus its linearization is upper bounded by a first order term plus a second order term, right? So just look at these terms, this one and up to here. So we have this 1 over 2 lambda k from the line above, right? And the other term here is just minus L over 2, right? And this minus L over 2 and this minus 2m, they are coming from that smoothness condition on f, right? F minus is linearization bounded by the sum of these two terms. Okay, and now let's rearrange the terms in this inequality. The resulting inequality would be, then we have lambda k This is just by rearranging terms and multiplying the resulting one by lambda k. And now let's upper bound this term, this inner product, by using the Cauchy-Schwarz inequality. Then we will have, this is upper bounded by the two lines above. Okay, we just upper bounded by some of these two quadratic terms. And now, so here we have this term. This one is in terms of the distance between xk plus 1 and sk norm square. And here is the same thing, right? We need to combine these two together. Continuing this inequality, we will have Okay, this is just by combining this quadratic term with this negative quadratic term together. And then we have this new quadratic term. And now, comparing this one with our goal there, the difference is that we have a constant term here. We have this constant term here. So we just upper bound these two terms because this is actually a quadratic function in terms of this displacement. So you can upper bound this sum, right? It's like minus ax squared plus bx can be upper bounded by b is less than or equal to a plus b squared over 4a. Right, so here it's just b squared over 4a. And b squared over 4a, so these two are upper bounded by b squared is 4 lambda k squared, m squared, divided by 4a, that's 1 minus 2 lambda k l, which is exactly the constant there, right? So just these two terms together, they are upper bounded by this one. So that completes the proof. Here it's just algebra. We use nothing more than that optimality, complexity, and smoothness. And also, this is basically the algorithmic mean, geometric mean, MGM inequality, the one we use here. Okay, so this is for one step. After that, we need to take expectation. Any question about the algebra?
Why there's a 1/4 in the second term of Cauchy walls?
Oh, so because this is like a squared plus 1 over 4 b squared greater than or equal to ab. Right, this is, first we need to use we first need to use Cauchy and then again the AMGM.
Yeah, thank you.
Any question about algebra? So now we need to take expectation. here actually, even though I say it's complex, but this is the exact bound, right? Here I didn't ignore all these constants. This is the exact bound on the number of iterations, but I didn't make the claim here very rigorous. So the convergence is in this average point, right? Here is a combination of all the iterates we have. Now let's do the proof. Okay, so let's first take the conditional expectation. I will just simply write expectation of something. This means the conditional expectation. Condition on this sample pass, right? I'm taking expectation of the final inequality we had in the last proof. So we take expectation of this inequality here, but this term, these two terms become they have been upper bounded by the constant. So conditioning on C k minus 1, the sequence, this is deterministic, right? We only take conditional expectation on this one, and here it's a constant, so we just copy down that constant. And this term goes away because conditioning on C k minus 1, this part is deterministic, so we only take expectation on this part because of the unbiasedness of Sk, right? If you take expectation, it becomes the exact subgradient, so they cancel out. This term just becomes 0 after expectation, and we only have an expectation on the quadratic term, right? Just this one here. And if you use the assumption on the boundedness of the variance, this expectation is upper bounded by sigma square, right? We can just change this to sigma square. So after taking the expectation, the expression has been simplified a lot. Yes.
That was because the mean of that is 0. Why we changed that?
It's because of the assumption. The assumption is that as for any x, it has nothing to do with the mean. It's just this assumption. It's upper bounded by sigma square for any x. Okay, now let's take the total expectation. So we take the expectation with respect to this sample path. And use the law of total expectation. All the expectations become the total expectation. So then after this line, when I write expectation, it means the total expectation. But before this line, they all mean the conditional expectation. And then we have the recursive formula, right? Because if you do the summation of iterations, these two terms, they will cancel out, right? It becomes a tight scope sum. So, and then on the right-hand side, we can just keep the first term, right? Just have the expectation of x0 minus x star, and then it's not the expectation because x0 is given, it's an input, so it's deterministic. So the right-hand side becomes totally deterministic. And the left-hand side, because of the convexity of the function phi, so, and also it's because of the by Jensen's inequality. Because of Jensen's inequality and convexity, so we can lower bound the left-hand side, the summation of, so after you sum, the left-hand side becomes summation lambda I phi of x I plus 1. Right? This one can be lower bounded by summation lambda I times phi of x k bar. Right, using the definition of k bar there, which is a convex combination. Right, you can use Jensen's inequality and convexity of phi to lower bound this summation by just a constant summation lambda I times phi of a single point function values, phi of x bar k. And then divide the whole inequality by sigma lambda I. We have the resulting inequality to go in the claim here. Just show this one in the end. And to finally obtain this this iteration complexity, you need to choose lambda to be small enough. So let's see. Now we have d0 square over 2 lambda k plus 4 lambda square times square 1 minus 2 lambda L times k divided by 2 lambda k. Right, this is the right-hand side we have. If you have constant subsize lambda I as lambda, right? And then you can simplify a little bit. This k goes away. Lambda cancels with one of the lambdas here, and 2 goes away. This becomes 2. And also here, k goes away, 2 goes away, and cancel 1 lambda. Right, this is the right-hand side after simplification if you take constant subsize lambda. Right, and if we here it suggests us to take lambda to be no more than 1 over 4L. So let's use the bound lambda is less than to 4L here. So this means this term can be upper bounded by (4m squared), right, plus sigma squared. Here is again d0 squared over 2 lambda k. Right, and our goal is to make this sum to be less than or equal to epsilon. So let's allocate epsilon over 2 for this part, and another epsilon over 2 for this part. Okay, the constant is a little bit different, but the constant doesn't matter very much, right? So this means lambda has to be smaller than or equal to epsilon over 2 divided by this constant. I did a different calculation somewhere, so that's why I have a 16 here, but 8 here. But if you do a careful calculation, there should be just one answer. But the constant is not the key. What's the key is the order. Here, what's interesting here is that it suggests to take the m to be on the order of sigma. So this is what usually happens in the analysis. The modulus for the non-smoothness is on the order of the modulus of the standard deviation. So m is usually believed to be approximately sigma, because they are both like a bound on the subgradient. This m is a bound, more or less like a bound on the subgradient f prime, right? F is a bound on the size of f prime, and sigma is like a bound on the sxk. Right. This is from the assumption, the boundedness of the variance. Right. Sigma is like a bound on the difference, and m is like a bound on f prime. So intuitively, these two should be on the same order. Right. That's why we have both m squared and the sigma squared showing up. They play the same role. And also, on the other side, to make this part small, you cannot. Taking lambda small is not enough. Taking lambda small will make this term to be large, so we need to take k large, right? So we need d0 squared over 2 lambda k I star equal to epsilon over 2. So that suggests us to take k to be on the order d0 squared over lambda epsilon. Right, and then we plug in the bound on the choice of lambda. It gives us this k. This k comes from d0 squared over lambda epsilon, because lambda has the form of a mean, so the inverse has the form of a max. And that explains why we have the max for the bound on k. Okay. So that completes the analysis on convergence expectation. Usually, when you have convergence in expectation, one step further is to get some results for the convergence in probability. Can you say some probability bound on the function value gap, right? And that can be simply done by using the Markov inequality. So we have the following corollary. So for high probability bound, our goal is usually to find a good solution with high probability. But here the probability is at least 1 minus p. P can be a small value close to 0. Then it's a high probability. And what you want to achieve is the primal gap, the function value gap is no more than epsilon. What we say there is expectation, but here it's stronger, right? It's an implication of the expectation result. So starting from the expectation result and use the Markov inequality. So let's first assume we have this result. Suppose we have expectation less than or equal to p times epsilon. So this is a stronger result because it's scaled by a smaller value p, right? So this is a tighter upper bound, right? Because p is smaller than 1. So with this and together with the Markov inequality, right? So the first inequality is just Markov. Probability of something greater than or equal to epsilon is expectation of that something divided by this tolerance epsilon. Right? And here we assume this expectation is no more than p times epsilon. So this ratio is upper bounded by p. Right? Expectation of this primal gap greater than or equal to epsilon is less than or equal to p is equivalent to say this gap is less than or equal to epsilon with probability at least 1 minus p. Right? That's the complementing event. Right? And so to achieve this goal, this is the same goal as here, right? To achieve this goal, a necessary condition, a sufficient condition is this, right? Is this to happen. And then the complexity of this one is just by replacing the epsilon by p epsilon in that complexity bound. So we obtain this final complexity. But if you take a closer look at this bound, it's ruined by this p. If this p is very close to 1, say 10 to the minus 6, then this is scaling with 10 to the 12, right? This is scaled by 1 over p squared, the max of the 2. Right? Then this, if p is small, then this ruins the complexity. So our goal is to find the complexity bound such that it scales with not 1 over p, but the logarithm of 1 over p, just log 1 over p. That will be better, right? Even if your p is 10 to the 6, 10 to the minus 6, this part is still constant order, right? That's a better result. But usually that that requires a stronger assumption on the noise. Right now we just assume the bounded noise, the bounded variance, right? The expectation of S minus F prime norm square upper bounded by sigma square. That's a very weak assumption. So if you want to achieve higher complexity, higher probability, usually you need to assume some light tail assumption. For example, we can assume a subgaussian distribution of the noise. So that's the second part of SA. It's the high probability result, convergence for high probability, but with stronger assumption. Okay, first we need to strengthen the assumption on the noise. So we now assume a light tail distribution. We assume, for example, we assume subgaussian distribution. That means the expectation of this exponential exponential of this distance, subgradient distance square, norm square divided by sigma square, and then take the expectation. This is no more than the natural number e, right? This is expectation of 1, just e. And actually this implies what we assume that the bounded variance. This implies that as this is less than 2 sigma. So this comes from this, the following simple fact. Suppose you have a random variable x, and expectation of exponential of x over a is upper bounded by exp of 1. Right? This x can be viewed as this norm square here. Right? This a is just the sigma square, and we want to show that what we want to show here is just the expectation of that x less than or equal to a. Right? That's what we want to show. So by Jensen's inequality, we have expectation, exponential of this expectation is no more than expectation of the exponential, right? Because exponential is a convex function, right? Then the convex combination is always, convex combination of the function values is always upper bounding the corresponding function value of the convex combination of the points, right? So this is the Jensen's inequality. And then here, just by assumption, right? From here to here, it's just by assumption. And then comparing the first and the last term, you can take out the common exponential, right? What's left is just the expectation of x over a upper bounded by 1. And because a is just a a scalar, a deterministic number, we can multiply by a. So we have the claim, which is proved here, right? So from here, we can derive the assumption we had before. So this is a stronger assumption, right? We are making the assumption stronger so that we can achieve a better result. Before we show the hyperview result, we need the following lemma. I will skip the proof, but I have the complete proof in the notes. So the CK is a sequence of IID random variables. And then we also have a sequence of functions, zeta k. The notation here is kind of abstract, but it will be clear in the proof. Zeta k is a function determined depending on the sequence of randomness, ck. And for zeta k, we have the following two assumptions. First, conditioning on the sequence ck minus 1, zeta k is 0 after expectation. This is a conditional expectation. But this expectation is over the ck, conditioning on the past condition and then the expectation of the ck. And also, so this part is more or less like the generalization of the unbiasedness of the subgradient, and this part is like the sub-Gaussian tail, right? So here, sigma k, which can be viewed as sigma, we will take sigma k to be constant. It's just the sigma over all the k's. So here, beta k square over sigma k square, and then take the exponential, conditioning on the past information, ck minus 1, and then take expectation. This is again expectation with respect to the ck. This expectation is upper bounded by a constant, just the e. Right. So given these two assumptions, we can show a hypervective result, which will be useful in the final complexity analysis. So for any given negative scalar gamma, the summation of zeta I greater than or equal to gamma times the square root of the sigma I, summation of sigma I square, is upper bounded by this constant. This is basically this is proved by Chernoff bond. It's again another concentration inequality. So I will skip this technical proof, and let's see the final result for the hypermobility bond. So here we need to assume additionally that the domain for H is bounded. We assume a bounded diameter D, finite diameter. And then similar to what we have here, we need to have a scalar gamma. So for every gamma greater than to 0, we have this convergence for the average point, the combination we defined before. For this point, the primal gap for the probability is such that the primal gap to be greater than to this quantity. This is upper bounded by the sum of these two exponential numbers.
Wait, what's the symbol next to the gamma in that last? No, the two parentheses.
1 plus gamma.
Oh, 1 plus gamma.
So here, if you want to make this tolerance, which is like the epsilon, if you want to make this epsilon small, you need to take the gamma small, right? But taking gamma small will result a larger. The gamma small will make this upper bound to be large. So can we see? Maybe I can present another corollary. Yes, it will be clear in the corollary. The complexity will be. So let's take lambda k to be a constant again. from this theorem, we can derive the following corollary. If you take lambda to be a constant, every lambda k to be a constant lambda, as this minimum of the 2, then to find the hyperboreal result, we need complexity this much, right? So comparing, remember that previously what we have for this term, it was this divided by p, right? We had a p in the denominator. So previously we had a p here. And for this part, previously, here we need a bracket, I think. Yes. So previously, when we just simply use the Markov inequality, for this part, we don't have this log 1 over p here, but we had p squared here. And we didn't have this term. This can be, basically this will be dominated by these two terms. But this term basically was the dominant part, right? It was 1 over p squared, but now it's just log of 1 over p, right? This is the improvement we're looking for. And this is achieved by this theorem. And it's because the reason why we have this improvement is because of this sub-Gaussian assumption, right? And also with help of this technical result. Basically, this technical result will give you this exponential here. And the other part comes from the smart usage of the Markov inequality and also the sub-Gaussian assumption. So this comes of summation of two property bounds. I think I will have to stop here. I need to go to the airport soon. So let's catch up the proof next time.
We have an extension for the homework to Sunday.
The homework will be due next Thursday, right?
Yeah.
So you still have one more week.
Yeah, these 2 weeks are quite crazy to me. And the homework,
Can you try to? Let's try to wait until Tuesday, next Tuesday,
Okay.
and see if you have done like much progress, and
Okay.
otherwise we can try to give an extension.
Okay.
Okay.
Thank you.
Try to work hard before next Tuesday.
Okay.
If you cannot manage to do it, we can try to give an extension.
Okay, thanks. A good trip.
Thank you.